Are we on? Okay, great. All right, welcome back. Today I will not be using the board, and the lecture slides you can download from the website already if you would like. But I encourage you to try to follow along rather than think that you can just look at the notes later. I think I'll say a lot of very interesting things. The last class yesterday we talked about some sparse matrix data structures. And one data structure that we talked about, which is probably the most well-known data structure, the most widely used, is called compressed sparse row. And that stored rows, stored it in a row major form. You could ask, well, how about compressed sparse column? That is also very widely used. So it's just a transpose of the data structure. And that format is in fact used in MATLAB. So you've been using some sparse matrices in MATLAB, and MATLAB uses compressed sparse column. So none of these things are that esoteric. And I thought it would be very fun to see the internal workings of the compressed sparse column format in MATLAB. So we'll do that. And one of the things that we will, one of the ways that we will do that is to use something called MEX files. Okay, MEX files is a way of calling C programs from MATLAB. Okay? And there are a number of reasons why you might want to do this. One is that C codes are normally much more efficient than MATLAB programs. Okay, so if you had a very expensive program to write, I have a pointer. Oh, you want me to use this one? Okay, now I feel I'm back in the 90s. So C code is much more efficient than MATLAB programs. If you had a expensive computation to perform, you might want to write a C program rather than a MATLAB program. But you might want to have the advantages of MATLAB as well, such as the easy interface. So you can call C programs from MATLAB. Some types of algorithms are easier to write in C than in MATLAB. So instead of writing a MATLAB program, you might want to write a C program. And an example could be any program that involves linked lists or pointers or things like that, dealing with elements of a sparse matrix even. And you may also want to use MATLAB to call functions in an existing C library. So someone gives you a C program library and you want to use it from MATLAB, you can link to that library from MATLAB. Okay? This is a very common way for me to use MATLAB, in fact, mixing C and MATLAB. So it's something that I think would be very interesting to, if you program in C at all, it's something very useful for you if you don't know this already. Okay, so the main idea is the following. So here's MATLAB, okay? And to access your C function, you need to write a wrapper for it, okay? And the MathWorks people call this a gateway function. And it is a function whose name is MEX function. And from the gateway function, you can call any other C functions, or your code might be implemented within your gateway function. Okay? And to see what this MEX function looks like, okay, this is every MEX function, every gateway function has to be called MEX function, and it takes exactly these 4 parameters. Okay? The first parameter, number, is the number of objects on the left-hand side, and this is the number of objects to return. Okay, MATLAB can return more than one object. And then P, left-hand side, is an array of objects to be returned. So P, I think, stands for pointer. So pointer to the left-hand side objects. Number of inputs, number of things on the right-hand side. Okay, and a pointer to the right-hand side objects. So to make things really clear, so let's suppose that we have a function that we wrote that we're going to call called AddMix. Okay, so you don't have to call your functions MEX. I just do it because I like to know that I'm calling a MEX function. So normally when I write a MEX function, I use _MEX at the end. So this function takes 2 arguments, so 2 inputs and 1 output. Okay, so number of objects on the left-hand side is 1. And what it does is it's going to just add two numbers together, add A and B together and return A. Okay, so to compile this, we're just going to use this MEX program, use this MEX compiler, let's say, from the MATLAB prompt. And we're going to do this right now. And you can also download AddMix yourself from the web page. Okay, and then we'll do some other examples. There's two other examples over here as well. So here you see that I already have my AddNextC. So let's look at what AddNextC looks like. So this is my gateway function. Okay, so as I promised, MEX function has exactly this signature. Okay, and this is how I use it. Okay, so first I'm going to print the number of left-hand side objects and the number of right-hand side objects that it was called with. Okay, so I will expect this to be 1, and I will expect this to be 2. Okay, and then P pointer to the right-hand side, these are going to point to my arguments in order. So there will be B and C. Okay, and this function returns a pointer to the data. Okay, and I dereference that pointer to store that into B. Similarly for C, and I can print B and C inside my C program. I'm going to compute A plus B. So this is all the computation that is being done here. I could call another function to do that, but this is the computation. And then I'm going to create an object to return on the left-hand side. There's only one of them. Okay, and I create that using create double scalar, and I'm going to put A inside there. So this A is going to be returned. All right, so to compile, I'm going to type MEX AddNextC. Okay, so it compiled successfully. And then I can run the program, AddMix. So what two numbers do we want to add? Say 3.1 and 1.1. Okay. All right, so the number of things on the left-hand side is 1. So it found that I had one thing on the left-hand side, two things on the right-hand side. It printed B and C, right? And how about the answer? Should we check that we got the right answer? And we got the right answer. Okay, so this is a very good template that you can use to write your own MEX programs. The arguments are just scalars, but in general, the arguments could even be matrices, and there's lots of documentation on the web to tell you about what these functions should be for different matrices. Okay, any questions about this so far?
Sir,
yeah.
This presentation, we can use the normal C structure with this presentation. I mean, with this format, normal C structure. I mean, say if I define full structure for a C program, and I want to call that particular C program being called in a particular part of a MATLAB function, MATLAB program. Can I do that?
So you can use any functions and any data structures that you define in C. So I've created a function called AddNextC, right? And from MATLAB, if I use AddMix, it will automatically call this gateway function. And then from this gateway function, you can call anything you like.
Yeah, I mean, I'm saying that if I make this gateway function as a timer to other functions, I mean.
As a what to other functions?
Say I make a gateway function which will use other two functions within that function. I can do that too.
Other two C functions.
I can do that.
Yeah, so this program can call other functions.
Yes.
Not everything needs to be inside here.
And that other function can be some library or something.
And that can be a library function. So you're impressed. This is very useful to you. So if you like using MATLAB, and you want to use MATLAB with other codes, then you can do that. Yep.
Do you mind to show an example of the other way around, the reverse of the MATLAB code, and then generate to become a C code?
I don't have an example like that handy, but the question is, suppose you have a C program, right? And you want to use some functionality in MATLAB. So MATLAB has functionality to compute singular value decomposition. It can have, you can have M files that you've written.
No, I meant if I'm writing the code in MATLAB,
Okay.
and then converting it to C code, the coder, MATLAB coder.
Oh, I see.
Like for example, for this.
Okay, so that's yet another question. So over the years, MathWorks has created a lot of different things that you can do. So suppose you have a C program and you want to convert it into MATLAB automatically, or the other way around. You have a MATLAB program and you want to convert it to a C program.
From MATLAB code to the C.
Yeah, so I've never done that myself.
That's the app series.
But there's something in the MathWorks that lets you do that, I think.
That thing, I don't think that is working properly.
Yeah, so that is a hard problem. That is not easy to do.
That is, I think, problem dependent. For some
For simple programs, you may be able to do that. But for hard programs, you may not be able to do that. Okay. Any other questions?
So actually, I'm interested in what you just mentioned. So in C, you can code.
Yeah, so in fact, there's another way of calling MATLAB from C, just the other direction. And that could be useful too. Okay, I don't have an example of that. I don't use that as much, but I have done that. But there's documentation on how to do that on the web. Okay, so let's look at a more complicated example now, having to deal with sparse matrices. And this example you can also download. It is called dump matrix. Okay, and the purpose of this function is you're going to pass in a sparse matrix, okay, and we're just going to dump out the entries of the sparse matrix. Okay, in other words, we're just going to write out the non-zero values in the sparse matrix. So the interface is a little bit simpler because we only have one thing on the right-hand side. And what these functions do, so getM gives you the number of columns in the sparse matrix. GetJC gives us the column pointers. Okay, since it's in compressed sparse column format, this gives us the column pointers, the pointers to each column. This gives us the row indices. And this gives us the values. So this is the IAJAA, similar to the compressed sparse row that we saw last time. And then here is a loop to print out all of the entries. So we're going to first loop over all of the columns. Then for each, this is a loop over all of the elements in the column. And this is just prints out the values in each, the values of each non-zero in the column. Okay, so this shows you that when you pass in a MATLAB sparse matrix, underneath it's stored in this compressed sparse column format. Okay, and all of the algorithms applied to compressed sparse matrices use this format. Okay, so let's try that. Let's make a sparse matrix first. What sparse matrix should we use? So let's say we'll generate a sparse, random matrix, and then we'll make it sparse by sparse storage. A equals sparse A. Okay, so you can notice that I generated a dense matrix, okay, and when I printed it out, it prints it in this dense matrix format. It happens not to have any zeros. If there were some zeros, then they wouldn't be stored in this sparse format. Okay? And I can call my function dump matrix mex a dump matrix mex. Okay, well, what did I do wrong? I think I probably did not compile it yet. So mex dump matrix mex.c. And for this function, I need to compile with a special flag because I'm using sparse matrices called large array dims. And this is noted in the slides that I'm using today. All right, so now I've compiled it. Now I can try to run it. Okay, so there we go. Okay, so this is the output of my program, and you can see that it matches up with the entries in the original matrix stored on the MATLAB side. Okay? Any questions? Okay, so there's one other example that you can look at, and this is called matvec mex. And this is an example of a program to multiply a sparse matrix by a dense vector. Okay, so in other words, the common function that is used in, for instance, the conjugate gradient algorithm. Right? So here's the matrix and here's the vector. And here I'm checking that the number of parameters passed in is 2. Okay? And I'm going to create a vector as the output. So I'm going to create a double matrix of this size, n by 1. Okay? And then I'm going to call my own function called matvec with all of the parameters, pointers to the arrays in the data structure. And here's my matvec program, and I wrote pseudocode for this last time. Right? So here's the IA, JA, and A, looping through all of the. This is actually something different. So this is assuming that the matrix in CS is in CSR format. Okay? So it's actually going to multiply by the transpose. Okay? And one of the reasons why I do this is you'll notice that there's this funny line. I'm trying to parallelize, using multiple cores that I might have on my processor, the computation of the sparse matrix vector product. Okay? So the interesting thing is that the sparse matrix vector product in MATLAB is not parallelized. So when I asked them 2 years ago, it was not parallelized. I don't think that they have parallelized it. One of the reasons why I think that it's not parallelized is because they store the sparse matrix in compressed sparse column format. And that format, in that format, it's a little bit more difficult to parallelize than in compressed sparse row. In compressed sparse row, you can imagine that each component of the output, each yi, can be computed independently. Right? Whereas if you store by columns, right, then and you assign a set of the columns, a subset of the columns to one of the processors, for instance, then it's going to compute a partial sum. And somehow you have to combine all these partial sums to get the total output, this y vector that we've been calling. So, and in that case, that's harder to parallelize because that could be an expensive sequential step. Okay, so one thing that you can try to do is to write your own parallelized matrix vector product, but you have to assume that the matrix is transposed when you pass in your matrix. Or if your matrix is symmetric, then it doesn't matter. Okay, so this is what I often use. I have the simple program, MEX program, to multiply a sparse matrix by a vector in compressed sparse row format. And here I'm using OpenMP to parallelize this outer loop. So this outer loop is over n iterations, and OpenMP will automatically partition all of these iterations to the different processors or the different cores that are available. Okay? I could demonstrate this on my laptop, but my laptop only has 2 cores. I actually checked. I didn't know how many it had. So maybe if we have time at some point, we could try to run it on a server that has like 20 cores, and you will see that there's definitely a speed up. At least on my at least on the servers that I have with MATLAB, about a year or 2 older, I definitely see a speed up. Okay, so that's something that you can also download and play around with if you have some experience with C and you want to try MEX file programming. Okay, any questions? Okay, so that's what I wanted to show you about MEX file programming. What I want to do today is to talk a little bit more about sparse matrix data structures and more advanced concepts. So last time we saw the coordinate format and the compressed sparse row format. And we'll see more advanced formats. And I want to at the beginning point out this paper. And I've stolen a number of figures from this paper. I think the figures in this paper are done really well, and some of the explanations are done really well. So this is something you can refer to as well. So recall that when we have a sparse matrix data structure, the non-zeros are not generally stored. Okay? And that the formats are generally optimized for sparse matrix vector product computation. Okay, so we said this last time. And here are a few computational considerations. So to perform the sparse matrix vector product, we have to traverse all of the matrix A. Okay, and we saw that the access pattern for that is fairly predictable. However, accessing memory is slow anyways. And sometimes it's slow enough that people generally view this computation as being limited by memory bandwidth. In other words, being limited by how fast you can access memory. Okay, so it doesn't even matter how fast your computer can perform floating point computations. It really just matters how fast you can access memory. However, on many accelerators such as GPUs and on coprocessors such as Intel Xeon Phi, memory bandwidth might not be the limiting factor. There may be other things. You know, on these things we have a lot of cores and relatively slow cores. Okay, and the memory bandwidth could be not the limiting factor. It could be some other types of overheads. Okay, to try to speed up the computation on these accelerators and coprocessors, you have to use a type of programming called SIMD, which stands for single instruction multiple data. And that means you have a single instruction which will perform multiple things at the same time. So for the purposes of our discussion, let's say a single instruction will perform 4 things at the same time. It will access 4 words of data all at once. It's generally much more efficient to access 4 words of contiguous data at once rather than to access arbitrarily 4 different words. And it will do multiplication, addition on these 4 words simultaneously. And it is also desirable to use long loops rather than short loops. Okay, and we'll see an example of this in a moment. Okay, and if you do use SIMD, the computation can be so efficient that using just a small number of cores on your processor, let's say just 2, if you have 10 cores on your processor, maybe only using 2 cores on your processor, you can saturate all of the bandwidth, meaning you can use up all of the bandwidth that is available to your processor, and using more cores will not actually help. Okay, so in that case, you can actually save energy. So you could, let's say, turn off the remaining 8 cores and just use 2 cores. Okay, so these are some reasons for trying to make the computation more efficient, even though we generally view the computation as being limited by memory bandwidth. Okay, so
Very first, you mean zeros are not generally stored?
oh yeah, this is right. So zeros are not generally stored. Sorry about that. I'm going to have to try to fix that. Remember to fix that. Okay, so here is a picture of the CSR format. So here is a sparse matrix. You can tell that this matrix, well, you can maybe tell this matrix is not from finite differences. It's just some arbitrary sparse matrix, right? And this is the CSR format. So each row is stored. So in the first row, there are 4 elements stored. They're stored contiguously. Then we store the next 4 elements on the next row. Then we store the next 2 elements on the next row, right? And the colors don't really mean anything. In this matrix, the second element of the second non-zero is colored red. So you can see that the second non-zero element lines up in this format. So this is a picture of what compressed sparse row format looks like. Okay? And if we look at the code for performing sparse matrix vector product with that format, it looks like this. This is what I wrote down last time on the left. Okay? Although this program doesn't use IAJA, maybe slightly more descriptive names. First is a loop over all of the rows. Okay? Then a loop over all of the entries in the ith row, where RPT stands for the row pointers. Right? So we're going to look at the beginning of the ith row and loop to the beginning of the next row. Okay? And then here is the accumulation into the ith component of the solution, the ith component of the product. Okay? So here's the x. This is the component of x that is multiplied. And val is the entries in the matrix A. Okay, so I wrote this down last time. Now, if we wanted to do 4 operations at once, okay, the compiler is expected to do this for you automatically, but conceptually, this is what happens. Okay, so you can see that here we have the loop over the entries in a row. Okay, but instead of doing 1 multiplication and accumulate at a time, we're going to do 4 at a time. Okay, so we have 4 different temporary variables. We're going to add these temporary variables together to get the result for the ith component. But we're going to do 4 of these at a time. And the idea is that there are instructions on these cores that allow us to do 4 in the same amount of time as it takes to do 1. Okay? And if the number of non-zeros in a row is not a multiple of 4, let's say we have 6, right? Then this loop is going to execute once, and then we have some leftover stuff. We have 2 left over. And we're going to do the 2 left over in this remainder loop, okay, which is not vectorized or which does not use SIMD. Okay? So you can see that we want loops to be long. If the loops are short, right, for instance, as in this picture, okay, we'll do 4 in one instruction, 4 in another instruction. Over here, we just use the remainder loop. Here we do 4, and then we use the remainder loop. So the remainder loop is used a lot, right? The remainder loop is used a lot relative to the number of times we execute this loop if the rows are short, right? And if the rows are short, this summation over here is also a relatively large proportion, takes up also a relatively large proportion of the time. Okay, so this is good. This type of thing is good if the rows are really long. Okay, but we don't control the length of the loops, right? The number of non-zeros in a matrix, that comes from the matrix discretization. So the question is, can we come up with, especially for these GPUs and coprocessors, can we come up with a better sparse matrix format? And one thing that we look for is a format that has longer loops. Okay? So here is one that has longer loops, and it is called the Lpack format. And it's actually a relatively old format that people used to use on vector supercomputers, but it has become popular again because of accelerators and coprocessors. So here's the same matrix, and here is the CSR picture that you saw a moment ago. And here is the Lpack format. Okay, so the Lpack format stores all the entries in a dense array. Okay, so here we stored everything like this. All of the rows have different lengths. We're going to store everything in a dense array. but we're going to store the entries in column major order rather than row major order. Okay, so we're going to store all the entries by column. Here the entries are stored by row. Here we're going to store the entries by column. Okay, so now we have a lot of long loops, right? So if we had a matrix that was 1,000,000 by 1,000,000, so these loops are now 1,000,000 in length rather than across here, which might be 5 in length. Okay, so now we have a lot of really long loops. And if we have rows that are different lengths, then there will be zeros here that are going to be stored explicitly. Okay, and that's called zero padding. If the rows are all about the same length, then we don't have to have a lot of zero padding. But if we have a matrix that has short rows and long rows, like in this example, then this format is not very efficient because it has to store a lot of these zeros. We're going to operate with these zeros, and we're going to have to move these zeros in memory, which is also very expensive. Okay? So for finite difference matrices, like we have been using, almost each row in 2D has 5 non-zeros. Lpack format is very effective. Okay? But if you have other types of matrices, then the format is not as effective. Okay. What people generally think about when they look at this picture is how can we change the Lpack format so that we don't have to store so many zero entries, because storing all these extra zero entries is something that hurts performance. As I said, extra computations and extra data movement. Okay. So potential solutions for the zero padding problem. Does anyone have any ideas? Anyone have any ideas on how to change the format so that you don't have to store so many? If you have an idea that someone else has not thought about already, then you can write a paper. And it's almost guaranteed to be published. There's so many people working on this. It's such an important problem. There's so many people working on it. So here's a possibility. Suppose that you have rows, all of them have 5 non-zeros in a row, and then you have one really long row that has like 1,000 non-zeros in that row. All right. In that case, what do you think is a good thing to do? Yeah, so you can just split up your matrix into 2 parts. One part is the regular part, and one part is the irregular part. So that's the first solution, which is a hybrid format. Unfortunately, this has already been invented, so you cannot write a paper on it. It's used on GPUs. I think it's in the NVIDIA GPU sparse library. And it uses Lpack format, okay, plus coordinate format. So coordinate format we saw last time, right? You can just store arbitrary non-zeros, right? So somehow you decide what is the regular part and what is the irregular part. And this idea, I think, is a paradigm that occurs often. In other words, you have an irregular problem. Let's try to split it up into some part that is regular and some part that is irregular. And hopefully the irregular part is small, because that's going to be expensive to compute with. And the regular part, we can compute fast. Okay, so that is an idea that is used over and over again. Okay, another idea is something called the jagged diagonal format. And I'll show you that in a moment. And a third idea is something called the sliced Lpack format. So we're going to see these two in a moment. Oh, and then there's a third, I guess, which is a combination of sliced Lpack and jagged diagonal format called cell C sigma, invented relatively recently by some people in Germany. Okay, so this is jagged diagonal format, which is actually also kind of old. Here's the matrix again. Here's the Lpack format. Okay. And what jagged diagonal format does is it sorts the rows by decreasing number of non-zeros. Okay, so we're going to find a row that has the most non-zeros. It's this one. So we're going to put that at the top. And then the next one is this one. We're going to put that next. And then the next one is this one. We're going to put that next. And you can see that there are 3 rows that have exactly 1 non-zero. So we're going to sort. So we're going to sort the rows. It's another reordering. Okay. And now the accesses, we're going to also store the number of non-zeros in each of these columns. Okay. And if we do that, then we don't have to store all these extra zeros. Okay. There is a disadvantage of this jagged diagonal format, and that is because you change the order of computation, you're going to change the order of accesses into the x vector. And remember, we want to choose the ordering of the matrix so that the accesses to the x vector are as friendly as possible to the cache, right? So this, because it changes the ordering, could damage the cache usage. So you may think of, well, there's actually a solution to that as well, which we'll see in a moment. Okay, so this is called the jagged diagonal format. Here's another solution. Okay, and this is called the sliced Lpack format, and this is a relatively recent solution. So here is the Lpack format. Okay, remember it's a dense matrix, and we're going to slice this dense matrix into chunks. And in this example, we're choosing chunks of 6 rows. Okay, so we're going to pick 6 rows, and we're going to slice it. 6 rows and slice it, 6 rows and slice it. And you can see that in each chunk, we're going to use Lpack format, right? But some of the chunks have the longest row in each chunk could be different, right? So here, the longest row in this chunk is this one. We have to store all these additional non-zeros. But in this chunk, the longest row is shorter. Okay, so we don't have to store as many non-zeros. Okay, so we have the Lpack format and we've sliced it. And this avoids the problem of irregular access of x because we're using the same ordering. Right? You give it an ordering in which accesses in x are efficient. This uses the same ordering. Any questions about this so far? Okay.
So the performance still depends on the sparse. We have some irregular values, some long one, and then some short one, and long one. Something like that first two, then still.
Yeah, so we're still going to have to store some. This doesn't completely get rid of the zero padding problem, right? But it reduces the amount of zero padding. So in jagged diagonal, we've completely removed the zero padding. So this could be good if storage is much more important to you.
So in practice, does that really keep 2 copies of the matrices?
Do you keep 2 copies of the matrix? There's definitely a conversion that has to occur. So your application might give you a matrix in a certain format. And if you want to use any of these formats for sparse matrix vector product, and it's not the same as the format that, that the application has given you, then you'll have to do the conversion. So that's an additional cost. And people do take into account this cost when they're considering these different formats. But often it is worth doing the conversion because you're going to, for instance, in the conjugate gradient algorithm, multiply by this sparse matrix many, many times, right? And So the cost of doing the conversion is amortized over all of the times that you have to do the multiply.
Can we do the permutation first before we commute? If we commute to the rules, then maybe somehow we can get rid of some more zeros.
Yeah, so that is a really good idea. So that is the hybrid of jagged diagonal and slice Lpack called the cell C sigma format. And if you had this idea 3 years ago, you could write a paper,
Too late.
but you're a little bit late. Okay, so this is the cell C sigma format. So here is sliced Lpack. So cell stands for sliced Lpack. That's what that means. So this is sliced Lpack, right? And we're going to do some sorting, just like in jagged diagonal, okay? Right? Because if we do the sorting, you can see that it tends to group the rows of similar length together, right? So this can be much smaller now than before. So, whoops, I guess I had it over here. So this was actually pretty large, but because we sorted, this total area is smaller than this total area, okay? But the interesting thing is that instead of sorting all of the rows together, we only sort within a window. So in this example, we're sorting in a window of 12 rows. Okay? And the reason for doing that is that we don't want to have some row potentially be moved anywhere in the matrix or done at any time. So it will only move a little bit, right? And imagine if you had a banded matrix, okay? If you have a banded matrix and you're going to move some of the rows, the matrix after you move some of the rows will still look kind of banded. The bandwidth may increase a little bit, but it'll still look kind of banded, okay? And because it still looks kind of banded, the access to X is still going to be fairly efficient. Okay, so the main reason for not sorting the entire thing together and to use these windows is to help preserve locality in accessing X. Yep.
How are we deciding the width of the window? For here you took 12 cells, something like that, right?
Sorry?
I'm saying that how are we deciding the width of the window?
Okay, so that's a really good question. How do we decide 12 in this example? How do we decide the sorting window size? Similar question to how do we decide what the chunk size should be, right? So I don't think that there is a good way to do this except to do some experiments for your different types of matrices. You want to choose a chunk size that will try to reduce the zero padding, right? You want to choose the sorting window size to try to reduce the amount of zero padding. But then there's a trade-off. If you use a sorting window size that is too large, then accesses to X might be inefficient because of poor cache usage. But if you choose it too small, then the padding, more zero padding may be needed. So you may need to do some experiments or analyze your matrix somehow to decide how to choose these parameters. But that is actually a very good question. It makes these formats a little bit difficult to use because you have to choose these parameters. If you don't choose them well, then you may end up with a data structure that is not that efficient for your matrix after all. Okay, any questions on this?